There is a factory in Fort Worth, Texas, where the roof covers 1.8 million square feet, roughly 33 football fields under a single structure. Inside, 15,000 people go to work every day building the most expensive weapons program in human history. The total cost of the F-35 program across its full life cycle, development, production, and maintenance through 2088 is projected to reach $1.7 trillion. That is more money than the GDP of most countries on Earth. And yet, for all of that, the F-35 is not built to be seen. It is built specifically to be invisible. This is the Lockheed Martin F-35 Lightning II factory. And what happens inside it defies almost everything you think you know about how aircraft are made. By the end of this video, you'll know exactly how it's made. The F-35 is not simply a fighter jet. It is a flying computer, a sensor platform with a weapons system attached. Its pilots don't look through a traditional cockpit glass and point the aircraft at threats. They look through the aircraft. 6 cameras mounted around the fuselage feed imagery into the pilot's helmet, creating a seamless 360-degree view of everything outside. The pilot can look down through the floor of the cockpit and see the ground directly below them. The aircraft's sensors fuse radar, electronic warfare, and infrared data into a single tactical picture that is shared in real time with other aircraft, ships, and ground stations. There are 3 variants. The F-35A is the conventional takeoff and landing version used by the Air Force. The F-35B is the short takeoff and vertical landing version. It can hover like a helicopter and land on a ship the size of an aircraft carrier, but without a catapult. The F-35C has the largest wings of the 3 and is designed for catapult launches from full-size carriers. 1 airframe design, 3 fundamentally different aircraft, all built on the same production line. 17 nations have either ordered or are actively flying the F-35. Over 1,000 have been delivered. The total planned procurement across all customers exceeds 3,000 aircraft, and every single one of them begins its life in Fort Worth. The materials that go into an F-35 are not the materials that built the fighters of the 20th century.
There is almost no conventional aluminum in the airframe. Instead, roughly 35% of the structure by weight is carbon fiber composite. Another 15% is titanium. The rest is a combination of advanced aluminum-lithium alloys, steel, and specialized materials whose exact compositions are classified. Carbon fiber for the F-35 comes primarily from suppliers like Toray in Japan and Hexcel in the United States. The raw material, carbon fiber prepreg, which is carbon fiber fabric pre-impregnated with epoxy resin, arrives at the factory kept in cold storage at around -18 degrees Celsius. It has a shelf life. Once it warms up and begins to cure, its window for use is limited. The supply chain that keeps this material cold, from the Japanese factory floor to the Fort Worth composite shop, is a logistics operation in itself. The titanium comes largely from domestic suppliers, but historically has included material sourced from outside the United States, a dependency that has received significant scrutiny from defense planners, given that Russia is one of the world's largest titanium producers. The Pentagon has worked for years to reduce that dependency, and the war in Ukraine accelerated those efforts dramatically. These materials are chosen because they offer the holy trinity of advanced airframe design: high strength, low weight, and, crucially for the F-35, compatibility with the stealth coatings applied to the aircraft's surface. Aluminum reflects radar. Carbon fiber composite, shaped correctly and coated correctly, does not. Construction of an F-35 does not begin as a single aircraft. It begins as dozens of separate assemblies manufactured across the United States and internationally. Northrop Grumman in Palmdale, California builds the center fuselage, the largest single structural section, containing the main fuel tanks and the main landing gear bays. BAE Systems in Samlesbury, England builds the aft fuselage and the tail section. The wings are built in Fort Worth. The engine, a Pratt & Whitney F-135, the most powerful fighter engine ever produced, is shipped from East Hartford, Connecticut.
This is a deliberately international supply chain. By involving suppliers in partner nations, the UK, Italy, Netherlands, Australia, Norway, Denmark, Canada, Turkey, the program created what defense analysts call political lock-in. Each of those countries has skin in the game. Each has factories producing components, workers whose jobs depend on the program, and governments politically committed to the purchase. It is industrial statecraft as much as aerospace manufacturing. When the center fuselage arrives by truck from Palmdale, a journey that takes days under careful escort given its size and value, it meets its wings and forward fuselage sections in a structure called the Final Assembly and Checkout Facility, or FACO. This is the heart of the Fort Worth plant. Inside the FACO, the aircraft moves through a series of assembly stations on a moving production line. But this is not a line like a car factory, where things move in minutes. Each station represents days or weeks of work.
Teams of technicians and automated systems work simultaneously on different aspects of the aircraft: avionics installation, hydraulic line routing, landing gear fitment, weapons bay door rigging. At any given time, dozens of aircraft in various stages of completion occupy the floor simultaneously. The composite structures arrive from their respective manufacturers with major components already complete, but joining them requires precision that borders on obsessive. The tolerances for mating the fuselage sections are measured in thousandths of an inch. Even a small misalignment affects the aerodynamic contours, and on a stealth aircraft, misaligned surface contours are not merely an aesthetic problem, they reflect radar energy, defeating the entire purpose of the design. The fasteners that hold the aircraft together are not the bolts and rivets you would find in conventional construction. Many are titanium. Many are installed with interference fits, meaning they are slightly larger than the hole they go into and must be driven or pulled in with hydraulic tooling, creating a tight compression joint that will not loosen under the vibration of supersonic flight.
A single fastener installed incorrectly, wrong torque, wrong material, wrong installation sequence, can create a fatigue point that propagates into a crack over thousands of flight hours. There are approximately 300,000 fasteners in a single F-35. But this is where the manufacturing gets truly extraordinary. Stealth is not a feature applied to the F-35 the way paint is applied to a car. It is baked into every dimension of the aircraft's geometry, every material choice, every manufacturing decision. The edges of every panel, every door, every access hatch, every weapons bay, are aligned to a small set of edge angles that scatter radar returns away from the source. Look at an F-35 from above, and you will notice that every line on the aircraft appears to run at one of only a few angles. That is not coincidence. It is a fundamental principle of low observable design. The application of the F-35's radar-absorbent coatings is classified. The exact formulations, the application methods, the layer thicknesses. But what is publicly acknowledged is that it is extraordinarily difficult to do correctly and extraordinarily difficult to maintain. Early F-35s had coating durability issues. The coatings, while excellent at absorbing radar, are sensitive to the thermal and aerodynamic stresses of high-performance flight. Areas near the engine exhaust, the leading edges of the wings, and the high heat zones of the airframe require special treatment. The facilities for applying these coatings are separate, controlled environments within the plant. The workers inside wear protective gear, not because of radioactivity, but because the chemicals involved in radar-absorbent materials are not substances you want on your skin or in your lungs. Getting this coating right is one of the hardest manufacturing challenges in the entire program, and it is one of the primary reasons that nobody else in the Western world has been able to produce a comparable fifth-generation stealth aircraft at scale. The avionics integration is its own manufacturing universe. The F-35 runs on an architecture called the Integrated Core Processor. At the time of the aircraft's design, one of the most powerful airborne computing systems ever put into a tactical aircraft. It runs approximately 8 million lines of software code. Managing the development, testing, and verification of that software has been one of the most expensive and time-consuming aspects of the entire program.
Every aircraft that comes off the line must have its avionics systems configured, loaded with software, and tested through a procedure called System Verification Review. This is done in a specialized facility connected to ground simulation systems that can replicate the electromagnetic environment the aircraft will encounter in combat. Radar signals, missile guidance frequencies, electronic warfare scenarios, all simulated and injected into the aircraft's sensors while it sits on the ground, so that every response of every system can be verified before the aircraft ever flies. The helmet. The pilot's helmet is worth pausing on. The F-35 helmet-mounted display system costs approximately $400,000 per unit. It is custom-fitted to each pilot. It contains inertial sensors, display projectors, cameras, and electronics that allow it to show the fused sensor picture of the outside world in the pilot's visor. Early versions had image jitter problems at night that grounded the aircraft under certain conditions. Fixing those problems required years of development and software iteration. Before any F-35 leaves the factory, it must fly, and not just once. Each aircraft goes through a series of acceptance flights, test flights conducted by Lockheed Martin and government test pilots that validate the performance of every system. These flights happen at Naval Air Station Fort Worth Joint Reserve Base, adjacent to the factory. The aircraft is fueled, armed with dummy loads, and flown through a series of maneuvers and system checks that would take days to describe in full. If anything fails, and sometimes things do, the aircraft goes back into the facility for troubleshooting and repair. The customer, whether it is the US Air Force, the Royal Australian Air Force, the Israeli Air Force, or any of the other operators, does not take delivery until every discrepancy has been resolved to their satisfaction. The records generated for each individual aircraft, its build history, its inspection records, its flight test data, its component traceability, fill the equivalent of multiple filing cabinets of documentation. Every part that goes into that aircraft is tracked back to its raw material source. If a batch of titanium is ever found to have a problem, engineers can identify within hours which aircraft contain parts from that batch, down to the specific component and its location in the airframe. Here are the numbers that stop you in your tracks. The Fort Worth facility operates around the clock, 6 and sometimes 7 days a week. The factory floor is so large that standing at one end, the far wall disappears into the ambient haze of the building's own internal atmosphere. Employees in some sections use motorized carts to traverse the distance between workstations. The F-35's Pratt & Whitney F-135 engine produces 43,000 pounds of thrust with afterburner, more than the maximum takeoff weight of some smaller commercial aircraft. It burns approximately 28,000 pounds of fuel per hour at full military power. A single F-35A costs approximately $82 million in current production. That figure has come down significantly from early production lots, which cost over $200 million per aircraft. The cost reduction is a direct result of production rate efficiencies. The more aircraft built per year, the cheaper each one becomes. The software running the F-35 has gone through multiple major updates, called blocks. Block 4 software, currently being fielded, adds new weapons capabilities, sensor fusion improvements, and electronic warfare enhancements. It represents more lines of new code than the entire original software suite. The landing gear of an F-35C is designed to withstand arrested landings that generate forces equivalent to 40 times the force of gravity acting on the gear struts, because carrier landings are essentially controlled crashes. Across the fleet, F-35s are operating on every major US allied deployment. Israeli F-35Is, modified with Israeli-specific systems and called ADIRs, have conducted combat operations, marking the first time a stealth aircraft has been used in actual combat. Japan has purchased over 100. South Korea operates them. Finland, Belgium, and the Netherlands have ordered them to replace aging fleets. Poland has signed for 32. The supply chain supporting the global fleet involves over 1,900 suppliers in the United States and internationally. Sustaining 3,000-plus aircraft across 17 nations requires a logistics and maintenance ecosystem almost as complex as building them in the first place. Lockheed Martin has established regional maintenance facilities, and there is an international MRO, maintenance, repair, and overhaul network being built to support the fleet through the 2070s and beyond. The Pentagon is already discussing F-35 service life extensions and capability upgrades that will keep the airframe relevant for 50 years.
An aircraft designed in the early 2000s may still be flying operational missions in the 2070s, upgraded, re-engined, running software that doesn't exist yet. When a completed F-35 rolls out of the Fort Worth factory and fires its engine for the first time, it is the product of something almost incomprehensible in scale. Carbon fiber woven in Japan, titanium machined in Virginia, electronics designed in California, software written across a dozen states, a fuselage center section built in the Mojave Desert, tail fins fabricated in Lancashire, England. All of it flowing into a single facility in North Texas, assembled by 15,000 people using tools and techniques that did not exist 30 years ago, into a machine that can fly at twice the speed of sound, evade radar, process sensor data faster than the human brain can interpret it, and survive in an airspace no aircraft of the previous generation could enter and return from. From raw fiber and metal to invisible supersonic warplane. From raw material to the most sophisticated aircraft ever built for mass production. This is what the cutting edge of manufacturing looks like. What detail from the F-35's production surprised you the most? The 300,000 fasteners? The $400,000 helmet? The classified radar coatings? Tell me in the comments. The answers might surprise you. If you want to keep going deeper into the most extraordinary manufacturing operations on Earth, hit subscribe, because the next factory we're walking into is just as mind-blowing.